got going. So first of all, thank you for all coming along to my talk. My name is Noel Welsh, and I'm a consultant at _, which is a Scala consultancy headquartered in the UK, offices in the US and Australia. Quick check, is the voice level okay? Do I need to? Yep, we're all good. Excellent. Okay, I'm going to talk about what I think are the most important things you need for using Scala. So something which will be useful if you're a beginning programmer adopting Scala, or hopefully something that's useful if you're like a team lead and you're trying to onboard new people to use Scala effectively. So ways to get effective with Scala with the minimal amount of work. Let's go on with a bit of motivation though first. So people often complain that Scala is a complex language. Like you see this on the internet quite often, on the forums and so on. And I'd like to have a quick survey here. Who thinks that Scala is complex? Put your hand up. I go. Okay, so a lot of hands went up there. I think there is a lot of stuff in Scala, right? So on this slide, I've got a bunch of things that I don't use very often, but nonetheless exist in the language. So these all serve a purpose, right? Self-types and all this kind of stuff. They do things, but then don't do things that I sort of use very often. So the question is, do I have to learn about these? Do I have to fill my head with it? Or can we do things in a different way? And what do I mean by like in a different way? I prepared a short video for you to kind of demonstrate the feeling I want in like a Scala programmer, really. So let's go. Okay. Oops, all right. Okay, that was Keyboard Cat. Who's seen Keyboard Cat before? Me, because I make these slides. Okay. Go Keyboard Cat. And there's actually a lot we can learn as a Scala programmer from Keyboard Cat. There's a lot to teach us. So I'm going to just show the video again. It doesn't seem like I can get controls up here on the screen. But I want you to pay attention to right at the beginning. We'll see Keyboard Cat just pause before it starts hitting the keyboard. So there's a little bit of thinking going on there. And then when Keyboard Cat starts hitting the keyboard, we see that Keyboard Cat's in a very happy place. So look, there's the thinking there. And then just wailing away at that keyboard there, not even looking at the keys you're pressing, clearly having a good time. And that's what I want programming Scala to be like Keyboard Cat. Okay. So how can we achieve this Zen-like state that Keyboard Cat so easily reaches? And this was the problem we had when we were writing our training material. So we have this book, Essential Scala. How can we strip down Scala to just the things you need to get people really productive really quickly and having a good time, not being overwhelmed with complexity, wondering what they're doing, banging their head against the type system and so on. And we decided that after some thought, there are really sort of 6 things you need to be a proficient Scala programmer. I list them here. We have expressions, types and values, objects and classes, algebraic data types, structural recursion, sequencing computation, and type classes. And I'm going to be talking about these 3 mostly today. So the first 2, expressions, types, values, objects and classes, are really kind of fundamental things. Most programs have some experience with them already. It's not stuff that you need to spend a lot of time on, and a lot of it is just learning the syntax, like what's the syntax for declaring a class in Scala, declaring a method, and so on. The 3 that I've highlighted are where things get interesting, is where you see the patterns come, and type classes are another very important pattern, but I don't have time to really go through them. They take another 45 minutes or so. So I'll talk a little bit about type classes, but not so much. And before I get into this, I have to say that it's not something that I have just created on my own. Huge thanks to the PLT team, who have been researching teaching programming for about 20 years or so. And everything I'm doing is basically stolen from the work they've done. So go look for them if you want to see this stuff done well. Okay, let's get on with it. Algebraic data types. So our first pattern. All right. The goal here with algebraic data types, big fancy name, but it's solving a simple problem, is to really go from a description of data into code that represents that data. And in the particular type of data we'll be dealing with is where we can model the data with logical ORs and logical ANDs. So let me give you an example here. Let's say you're writing some kind of analytics package. That's pretty common in Scala world, big data, etc. And it's for a website, and there you might model your website visitors as two cases. A website visitor is either anonymous or they are logged in. And these are two cases that cover the entire problem space. If you're not anonymous, you're logged in. If you're not logged in, you're anonymous. Right, so great. Very simple. And you can see these guys, this logical OR pattern here. And then we'll know certain things about users. So for like a logged in user, they might have some kind of ID, which might be a user ID in the database, or it might be an analytics package, more likely a cookie we gave them. And because they're logged in, we'll know things like their email address, maybe their name, and this type of stuff, password, whatever. And we'll know similar things about our anonymous users in less detail, maybe just an ID. So you see that here we have this kind of AND pattern. A logged in user has an ID and an email address. So two examples of the code, seeing the OR pattern previously and the AND pattern. Okay. Now, onto the key idea behind algebraic data types. And the idea here is, once you have this model in your head that we saw using logical ORs and ANDs, the structure of the code follows automatically. And the structure of the code follows the structure of the data in a keyboard cat-like style. So let me give you examples. So there are two patterns here because we had two things. We have the logical AND and the logical OR. And because we're functional programmers, we like big fancy words for things, just like algebraic data type. So what we're going to do is we're going to call the logical OR a sum type and the logical AND a product type. It makes it sound more impressive when we talk to our friends. So let's have a look at these two patterns. Product type. A has a B and C. That's kind of the abstract version, right? So we're going to see the abstract versions of these patterns, and then we'll go back to the example and apply them to the example and see how it works out. Okay, so in abstract, A has a B and C as our product type. How do we implement this? We do it like this. Okay, so we're defining a type A, and A has a B, so we have an instance variable, if you like, or a member of B of type B. And A has a C, so we have, again, a C of type C. Right. Hopefully, everyone's looking at this and going, this is very simple. That is kind of the point. The other pattern, the OR type, or the sum type, again, in abstract, is A is a B or C, and the code looks like this. We have a sealed trait here. So sealed trait A defining A, and B extends A, saying B is an A. And C extends A. C is an A. Again, hopefully seeing very simple stuff. And combine these together, sum and product together, make algebraic data types. Another great big fancy word, but a very simple concept, as we've seen. So let's go back to the example I started with and see how we'd implement that. Website visitor is logged in or anonymous. Okay, as soon as we see that, right, as soon as we got that model in our head, done a little bit of thinking, the keyboard cat thinking, then it's just keyboard time, right? Wailing away at the keyboard, blah, 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 blah. Apply the pattern, and this is what comes out in your happy place. Okay, and all this is, I've taken the pattern I showed before, and I've substituted visitor for A, anonymous for B, and user for C. That's literally all I've done, and that's the code that comes out. So very simple, very keyboard cat-like. Then we might say, like I said earlier, logged in user has an ID and email address. A anonymous user just has an ID, say, the cookie ID. As soon as we see this, we recognize the pattern here, the product pattern, and we can again just keyboard cat it out, and we get this here. Can't point, unfortunately, but you see we have on anonymous we define ID, and on user we define ID and email. So again, very simple stuff. Let's see another example. Calculation is a success or failure. Okay, so imagine we're writing some kind of calculator application, and we want to model the fact that some calculations can fail, like taking the square root of a negative number or dividing by 0. So calculation can fail or it can succeed. All right, as soon as we've got this structure in our mind, again, little bit of thinking, and then it's keyboard cat time, and out comes this. And again, I've just taken the pattern we saw before, substituted the names, and that is literally what's up on the screen now. Okay. You might say, well, a success has a value of some kind, a calculation that we're doing, and a failure maybe has an error message saying what you did wrong, division by 0 or something like that. As we do that, bang, out comes this. This is our AND pattern. Success has a value. I've just made an integer here. You can make it a double or a big decimal or whatever is appropriate. And failure, the message, I've just made a string or whatever, whatever's appropriate for the application. Just keeping it simple here. So here we have defined these sort of fancy things, algebraic data types, seeing they just come down from a few simple patterns. And the key point here is the structure. If we can model data with logical ORs and logical ANDs, which you can do in a lot of cases, we've seen some examples which are reasonably close to real things, and we'll see some more examples later. Lots of stuff in standard library, for example, option, try, list, so on, are actually algebraic data types. Then we can model them in code very easily in a way that's almost entirely mechanical, just applying a few patterns and you get this, the code falls out. So you work out in your head what the model should be, that's the thinking bit, and then the code follows in a straightforward manner. Okay. Now, our next pattern is structural recursion. Structural recursion goes hand in hand with algebraic data types. So once we define an algebraic data type, we need to work with it and do something with it. And structural recursion is the pattern for working with algebraic data types. So whenever you see an algebraic data type, you know that you need to deploy structural recursion to work with it. So to give you an example, this is what we just had before, calculation success or failure. And now imagine my task was to implement a method add. Right? So we want to add an int to a calculation. And we want to write the code for that. So we'll come back to this example in just a moment. Excuse me. But before we do, I just want to go through the abstract patterns like we did before, see the patterns in abstract, and then we'll apply them to this concrete example. Right. The key point behind structural recursion is just like in algebraic data types, how the structure of the code follows the structure of the data, we're getting exactly the same thing here. The structure of the code for processing an algebraic data type follows the structure of the data in the same way that the code to define it follows the structure of the data. There's a very strong parallel here. Now, in Scala, because it's an object functional language, there are two ways of implementing this pattern. You can use pattern matching, which is more of a classic functional programming technique, or you can use polymorphism, which is more sort of classic OO. I'll show you both and then talk a little bit about preferences. Okay. So here's an abstract algebraic data type which has all of the patterns in. It's got and the or. So A is a B or C, B has a D and E, C has an FNG, right? So that's kind of like a complete algebraic data type displaying the two sum and product patterns. And of course, we can implement this in code like so, by applying the patterns we've seen before. And now we'll see structural recursion on that. So firstly, using pattern matching. We have some kind of method which is doing something. I've called it do something. It's returning a value of type H, again, just some sort of abstract type H. And we see the implementation here, the structure of that implementation is following the structure of the code. So we had A is a B or C, and we have a pattern for B or C. So that's the first part of the pattern. Whenever you have an OR a sum type, in your pattern match, you have a case for each branch in that OR. So A is B or C, and there we have the case for B and the case for C. Okay, then we have the AND types, the product types. And we said B was a D and E, so B has a D and E, and we match on B and get those things out, and then we need to do something with them, which I've said do B there, and that is the problem-specific part. That's where we have to do a little bit of thinking. What I'm actually doing? What am I trying to do? Same for C. C has FNG, and I need to do something problem-specific there, whatever is the appropriate thing to do. Okay. So that is essentially, that's the structural recursion pattern using pattern matching. And again, The structure here is just following the data. We can do the same thing with polymorphism if we like. Here we define an abstract method, do something, and then we have to implement it, concrete implementations on each of the subtypes. And that's just the same thing. Again, do B and do C being the kind of problem-specific bits. Right, so returning to our example, if you recall we had calculation is success or failure. We want to add an int to the calculation. So we have this kind of signature in the code that's given by our problem, add an int. Straight away we can just keyboard cut out the skeleton for the structural recursion. Okay? Calculation success or failure, so we need to have a case for success and a case for failure. Success has a value, so we've got to match on that, it's V, and failure has some kind of message, so we match on that. And now we have to do a little bit of thinking. What's the correct thing to do on the right-hand side of the pattern matches here? And in this case, it's quite simple. Success, we just want to add on value. Failure, if we fail, we keep on failing. Right. So, summary here of structural recursion. Processing algebraic data type, you always use structural recursion in some variant. And that structural recursion pattern follows directly from the data type, from the algebraic data type, from the data model, if you like. You can choose between pattern matching and polymorphism. I generally prefer pattern matching like so. The reason being that it puts all the code in one place. It's easy to read and see what's going on. But you can choose whatever you like. Okay. So those two patterns we've seen. Algebraic data types and structural recursion, they go hand in hand. They're very useful. I've said lots of things in the standard library use them. You can probably think of models of your own, like if you're modeling like users, you probably have normal users and administrative users. Maybe administrative users are different types, like content editors and sub-editors and editors above them all, or whatever's appropriate. And this is all using this type of algebraic data types, logical ors and logical ands. A user is an admin or a normal user. An admin is a sub-editor or an editor, whatever fits your domain. You'll find them all over the place. Now I want to look at another pattern, another group of patterns, sequencing computation. Okay. I should say, are there any questions here about the first two patterns? Anybody dying to ask anything?
Yes, yeah? A remark. The final hypothesis not necessary.
Okay. The question, the remark was that final is not necessary. I like to put final in there because it means that nobody's going to subclass my case classes and implement strange behavior, which may be unexpected. If I want to have open extensibility, then I have other techniques, namely a type class would be the way to do that I prefer to use. I'll talk about that a lot later because you need to talk about, well, maybe we should talk one-to-one. We have a bit of a blog post about it, and it's a little bit more complicated. Okay. Anything else? Right. Sequencing computation. So what do I mean by sequencing computation? Well, we're going to see some patterns for sequencing computation, but first we really need to explain what I mean by sequencing. Yeah. So the key thing is, as functional programmers, all we really do is transform values. That's all that a functional programmer does, because we're not using side effects, or at least not in the main part of our program, maybe around sort of the edges. And when you don't have side effects, all you can really do is go like from A to B to C. And this is what I mean by sequencing computations. Now, A to B to C is very simple. This might just be function composition. But we'll see cases where there's a little bit more structure there, and we can use some kind of, we can pull out this structure and recognize some patterns to give them names. That's basically what we're doing. Giving names to some common patterns of sequencing things. Okay. So 3 patterns in particular we're looking at are fold, map, and flat map. Now, some of you, this will be stuff you already know. I often see new developers struggle with working out where to use map, where to use flat map, and I'm hopefully going to give you a bit of insight in how you can approach that, whether you're a new developer yourself or whether you're someone who's teaching people to become good Scala developers, how they can approach these problems, break them down into small pieces and work out what they need to do. Okay, so let's start with fold. Fold is a generic conversion, if you like. So you put in something of type A, you get something of type B out. I'm going to write it like so, A to B, using sort of graphical symbols, hopefully. Now, the thing about fold is it only works on algebraic data types. Okay? And because we know that structural recursion is the pattern for dealing with algebraic data types, we know that fold is basically going to be some abstraction over structural recursion. That's exactly what it is. Okay, so fold can only be defined for algebraic data types. But it goes like this. So here was the generic skeleton we saw for structural recursion of our kind of generic algebraic data type. A is a B or C, B has a D and E, and so on. And if you recall, I said on the right-hand side of the patterns, the cases, was the problem-specific bit. So what we're going to do, or all we're going to do in fold, is we're going to abstract out those problem-specific bits. Rather than defining them for each method we want to implement, what we're going to do is say, look, you as a user can pass in a function that does this problem-specific part. So take those bits, raise them up to be method parameters, and rename the method fold. And that literally is it. That is all you do in fold. Just passing the bits that go on the right-hand side. So let's see an example of that to make it a little bit more concrete. So we define algebraic data type. Say result is a success or failure. Bang, there's our skeleton that comes immediately from that. Success contains a value of type A, and failure contains nothing. Okay? So success has a value of type A, and failure has no value. Who's going to tell me what this is? Anyone? Right. Yeah, I think I heard a mutter from the crowd. It is option. I've just defined an invariant version of option. So it's not quite option in the standard library, but it has slight differences I don't want to get into here. But I want to show you that these algebraic data types are all over Scala. And things like option, which again people often struggle with, when you boil them down to what the essence is, they are just these very simple things. Okay, now let's implement fold on this result type or option. Start with the structural recursion pattern. Again, we just keyboard cat that out. Fold is going to return some type B. There's a skeleton. Abstract out the arguments. Right? And there we go. S, A to B, and F of some type B. And there is our implementation of fold. And it took Scala till 2.11 to actually get a fold implemented option, but we've just seen that your average house cat could probably bang it out in about 5 minutes. So it's quite a simple thing, really. And also, if you go look at how fold is implemented on Scala, it does differ slightly. It uses a few little features, multiple parameter lists and biname arguments. But this is the essence of what's going on there. Okay. So fold is the generic transform for any algebraic data type. If it has a fold defined on it, then you can do anything you want on that data type using fold. So you can transform a list any way you like using fold left or fold right. You can transform an option any way you like using fold. You can, if try actually had fold implemented on it, there we go for consistency again, then you could do anything you liked using fold. But it's not always the best choice. And why may that be? 2 reasons, really. Firstly, not all data is an algebraic data type. Although it's a very broad class of data, there are things that don't fit in this box. So, for example, future is not an algebraic data type. Data which is infinite lists are not algebraic data types. So there are a few things that don't really fit in here, so we can't use fold. The other thing is that sometimes just other methods are easier to use. So when we use fold, we have to specify what we're going to do with all the different cases. And sometimes we don't want to say that. So there are patterns like using option where you just want to say, look, if it's none, then just keep it none. I don't want to do anything with that. I just want to change the value that's in there if there is a value. And of course, we recognize these patterns coming up and again, over and over again. And we've given them names, and some of you know the names already. Map and flat map, of course. And they're easier to use than using fold all the time. So let's have a look at these other patterns, map and flat map, and see what they mean. Okay, imagine we have a result of A, or an option of A, if you like. So, for example, let's get a user from the database. there might not be a user for the given ID. So we have this user, which are represented by circles wrapped up in a box, if you like, which is the rectangle around it, the square around it. The idea being when you look inside the box, there may not actually be a value there. Maybe it may have failed. Okay. Then let's say we want to convert our user to JSON. Very standard thing to do in a web service. So this looks like this, say, give me a user and I'll give you back some JSON. Okay, circle to star. And our result is going to be a result of JSON, because of course we might not have a user, so that if we don't have a user, then we can't convert it to JSON. So we're going to keep nothing there, failure. So this is the kind of pattern this computation has. And we have a name for this pattern, and we can abstract it out and call it map. Right? So map in abstract is you have some f of A goes to B, and you get out an f of B. And that's what map does. So this is kind of like a little algebra you can work with if you're trying to work out what should I be using, map or flat map or what here. Look at the types. Do you have something that looks like an f of A? Well, what do you have? Do you have an A to B function? Do you want to get an f of B function? Sorry, do you want to get f of B at the end? Look at what you have, what you want to get out, and you have to work out what you need to do. Okay, let's see another example. We're going to get a user from the database. There might not be a user. And then we want to get the most recent order for that user. Now, a user may not have ordered, so they might not have a most recent order. So instead of getting back just an order, we get back an order wrapped up in a result, because there might not be one that's representing this. Okay, so our complete computation is going to look like this. Get a result of user. If we have a user, get their order, and we're going to end up with this result of order. Okay. And again, we can abstract this pattern and give it a name, and the name, of course, is flat map. And flat map in abstract is f of A goes to f of B, f of B. All right. So let me give you a little bit more complicated example and show you how you can use this kind of algebraic way of thinking to work out what exactly you need to put in there, where your maps and your flat maps and your folds go. So let's imagine we're running some kind of web service. We're going to write this endpoint, get order. You're going to give me a user ID, and I'm going to give you back an HTTP response of some kind, like a 200 containing some JSON, or like a 404 if something went wrong, or maybe a 500. And the structure of the computation is basically this. This is what I have available. I'm going to start with the user ID. So I've said that's what goes into my endpoint. You need to provide a user ID. Then we're going to go, given our user ID, we're going to go off to the database and get our result of user back. So we may not have a user for that ID. And given a user, we're going to go get their order. And of course, they may not have an order, so we get this result of order back. Then we're going to convert the order to JSON. It's just a pure function there. There's no possibility of failure. And then given our final thing, a result of JSON, we're going to go to an HTTP response from that. Okay, so let's break this down. The first bit, the user ID, we assume comes from outside, so that's not really in scope for us. And going off to the database, again, is just a straightforward call. But things get a little bit interesting when we get to here. We have a result of user, and we have a function which is going to take a user to a result of order. So in abstract, we have this type of thing. And the question is, what method do I use to sequence these computations, to join them together? And you can recognize a pattern from the previous slide, and it's flat map that we need here. Flat map works with this pattern and is going to give me back a result of order. Okay, the next step, I have this result of order, and I have this function from order to JSON. So what's the function I should be using to glue these two parts of the computation together? And again, in abstract it's this, and you can recognize the pattern from the earlier slide, and the answer here is map. Map is the right thing to use here. Glue these two computations together, and we end up with a result of JSON. Now the final thing, I have this result of JSON, I want to convert it to an HTTP response. In abstract, I have this type of shape. What am I going to use here? Well, there's no relationship between the input and the output. For map and flat map, you always had a box around both the input and the output. But we know this is an algebraic data type, so our final option is fold. and fold is the right thing to use in this situation. Okay, so fold converts between sort of arbitrary types. In map and flat map, you're always keeping that wrapper around. So the summary here is there are these standard patterns for sequencing computation. Map, FA, A to B, you get FB, flat map, FA, A to F of B, you get F of B at the end. And fold, which is generic, do anything, but only applies for algebraic data types. The other thing is, I've just snuck monads in there in the last 10, 15 minutes. And you can, and we do, teach monads to beginning students. You just don't need, as long as you don't scare people to begin with, it's all fairly simple. Okay. So, let me just talk a little bit about type classes, and then I'll be done. I don't have time to go through the whole thing. I just want to give you a feel for when you use type classes, which is the other important pattern. So, type classes are for what we call ad hoc polymorphism. Again, it's functional programs with like big pretentious words, and this is a pretty big pretentious one. But something that's maybe more you can sort of get behind, of course, this being socialist Europe, is to break free from your class oppressors. This joke didn't play very well in San Francisco. Who'd have thought? Okay. The main concern here is when you have something which crosses class hierarchies. So the classic example is serializing something to JSON, right? You have a bunch of classes that you want to serialize to JSON, but there's no useful common type. Of course, everything has any as a common type, but you don't want to implement something on any because it would be very unsafe. So you have a bunch of classes and there's no useful common type uniting them, but you still want them to have some similar behavior. So when you have that situation, you can abstract that behavior out to a type class. That's the tool to use there. And then what type classes allow you to do is implement this behavior in an ad hoc way. So you can basically pick and choose the types of the classes for which you're implementing behavior without having some kind of class hierarchy uniting them. That's all I'm going to say about type classes now. Okay, so just about done, just about time for food. Conclusions, I think Scala can be simple. Scala is simple if you use these patterns. You write code this way. I think the first 3 patterns that we looked at, that'll be about 90% of your code. You add in type classes, you'll get up to about 99% of your code, at least the way I write code. And the code you get out is very simple to read, it's very simple to understand, anyone can write it, and it's good code as well. It uses the type system well, you don't run into errors, problems trying to extend it, trying to work with it. Very simple. The second important point is that program design can be very systematic. I've shown you a bunch of patterns, and really we just do a little bit of thinking, what's the pattern we're applying here, and then bang, the code comes out straight away. So that's a very important thing. Let me just put in a small plug. If you'd like to read more, we do have the book I mentioned earlier, and there's a 15% discount if you use the code FlatMap. Yeah, so underscore.io, I'm sure you can go there, you can find Essential Scala there. So that's what I have to say. Let me wrap up by saying, be like Keyboard Cat and get to that happy place. And I'd like to now invite any questions you may have. Okay, some questions? Everyone's keen to get to the food, I understand. I missed out on the food last time because I asked a bunch of questions. And then, I know, it's a bad deal.
From your talk, I see that we should program Scala like we program Haskell.
Okay, so we should program Scala like we program Haskell. I know, it's not really a question. Statement, yes. No, it's not really true. Scala has some differences, and what I have given, they are very, very straightforward, very basic, elementary kind of functional programming patterns, if you like. The reason that we do these things is they work well with the type system. But what I find is okay, so my experience, when I started with Scala, I did a bunch of stuff with OA features and self-types and all this kind of stuff, and I found I just made a massive mess, and it didn't work. And when I used these patterns, things work. They're simple, and the code is extendable, and it's easy to work with. So my own experience is that really going down the OO kind of big class hierarchy route, it just doesn't work very well. The other thing, though, you need to look at is when you get into sort of OO patterns and advanced functional programming patterns, you actually end up in the same space. So a few talks ago, I was in a PagerDuty talk, and the guy was talking about his builder pattern examples, and he was building up all these conditions for his tests using this builder pattern. And really, what he was doing in FPLAN is you'd call a combinator library, and it's exactly the same thing. And give me an example from a different point of view. There's these type of interpreters in FPLAN called finally tagless interpreters, considered very sort of advanced topic, recently published papers. And they are really very, very similar to just sort of stacking traits, if you like, in Scala. It's almost the same thing. So what I find is that when you take what's considered sort of good OO design and good FP design, that they actually end up in the same place. They have different terminology, maybe a different route to get there, but actually the final destination ends up being the same. So I don't really see this as being just Haskell, if you like. Okay, that was a great question, by the way. Anything else? Okay, well, let's go get some food then. Thank you all.